Okay, first thing we'll address is what is electric current. This is a wire, and well, all of us, a current is flowing through it this way. What happens is somehow, now this is a conductor and there are conduction electrons in this. So force acts on them, and this force acts because when you do something like this, you are setting up an electric field inside, and that electric field applies a force on the charges, and that's what makes the charges move. So this is how the current flows. How do we measure current is the first thing that we'll want to talk about. This is a check post, meaning a cross-sectional area on which I'm keeping an eye on it, and I'll see what blizzard of charges go past it like this, penetrating that check post, at what rate these charges are flowing by. Now actually I'm not interested in the number of charges, but I am interested in the amount of charges and the rate at which charge goes flowing by. Suppose after my investigation, I find out charge is going at this rate. How will I report it? Suppose I say, is this all right? 5 coulombs is going past this, rushing past this check post per second. Is that a kind of reasonable report? Well, that is what we call as current. Just that this is given a new name honoring ampere, and it is called as ampere. And in short, we use capital A. So we say 5 amperes of current is going. By that, what do we mean? We mean 5 coulombs worth of charge is rushing past that check post in 1 second. Now, let me share with you how did I come to know in my investigations, what did I find which told me that the charge was going past at this rate. What I actually did was I waited for 10 seconds. So I found in 10 seconds, 50 coulombs flew by. So I concluded 50 coulombs went in 10 seconds, so per second charge was flowing at this rate. So such a calculation I call as current. So that's how I got 5 coulombs per second or 5 amperes. Now in general, it may not be 50, this may not be 10. So how will I write it? I'll write it, in general, I'll write Q by T, because that could be anything. So I'll write it with a variable name, and time of wait could be anything. So that is the electric current. But there's a problem with it, which I'll explain to you by taking that numerical example. You see, I found out in 10 seconds 50 coulombs went by. But since I was witnessing all this rush of charges past that check post, so I know a little more than just that. I know the detail of how that 50 coulombs went past in those 10 seconds. What happened was, in the first 8 seconds, out of 10 seconds, in the first 8 seconds, only 8 coulombs went by. Whereas in the remaining 2 seconds, last 2 seconds, the rest of how much? 42 coulombs went by. Now, if I were to do that kind of calculation on this first piece of data, then I get current as 1 ampere. And if I do it here, I get 21 amperes. So which of these 3 scenarios answers is correct? Was the current 5 amperes Or was it this or was it that? Now you know what the answer is. You see, by dividing the entire thing by this, all I get is average value of current. So this is average value of current as averaged over that 10-second span of time. Okay. So this gives me the average value of current. If you want the instantaneous current, you just cannot afford to wait for a finite time, because in the next, moment the current could have changed. This AC which we are getting in this room, alternating current, it cyclically changes from a top value to top positive value. Positive means one way and negative means the other way. So it goes from that to this, and it keeps fluctuating, and it does that 50 times a second. And in a cycle also it increases and decreases in magnitude. Its graph, as I think you well know, is something like this. So the instantaneous current is changing with time. It's changing all the while. So if you waited for any span of time, you will get only an average value within that time. So for such a situation, just like for instantaneous velocity, you do not wait for a long time like 10 seconds or finite time symbol for t seconds. We'll be better advised to use infinitesimal time. So we say dt time, infinitesimal time. Now in the infinitesimal time, no matter with what great rush the current is going, no matter how fast the charges are moving, if the window of time over which we check them out is so small, infinitesimally small, then only infinitesimal charge can go by, and this gives us instantaneous current. Okay, so this is the definition of instantaneous current. Whereas this was average current. So a simple question. Here the charge Q flowing by, I have a formula, mathematical formula, and the formula is 2t cube plus t plus 5. In this formula, t is in seconds and q is in millicoulombs. Question: what is the instantaneous current? Instantaneous, I don't subscript it with INST, whereas average current I subscript it with this, okay, or with this. So what is the instantaneous current at t is equal to 2 seconds? And what is the average current from t is equal to 1 second to 3 seconds? Now take your choice. Either you say, oh, I'm learning these new things, or say this. You say, okay, I is dq by dt. I met a similar animal in the earliest chapter in physics, motion in one dimension, and I had something similar, only the interpretation of that symbol was different. Such a thing is called as current. That thing was called as V, and that was dx by dt. And the present questions are as though somebody has given you the following. So if you compare this with this, you know what is X. It is a creature like Q is in this mathematical creature. So without associating further meaning to these things, you could say this question is as though in motion in one dimension or kinematics, I had X is equal to 2t cube plus t plus 5, where t was in seconds and x was in meters. And somebody asked you, what is the instantaneous velocity at velocity? Yes, current. So he's asking, what is the instantaneous current? So that, okay, similarly here, what is the instantaneous velocity at t is equal to 2 seconds? And a second question says, what is the average velocity from t is equal to 1 to t is equal to 3 seconds? Now, if you know how to do that, you just in place of, you just think like that, mentate like that, but write these values. Okay, just write q instead of x and the derivative runs the same way. Or if you want, you can do it here. So I'll do it here, okay? So what is the instant? Now, I, let's solve it this here. So I being given by dq by dt, this function of q, let's grab hold of this and give it that treatment. So we differentiate. So we get 6t square plus 1. Now that presence of t tells me the current is not constant but variable. It is changing from time to time. Then I read his question. He says 2 seconds. I want the current at 2 seconds. So I say, therefore I at 2 seconds is, substitute t is equal to 2, and I get this for the answer. Sorry, this was millicoulombs. So let's go back here. Whatever is the unit of q is also the unit of dq. Because the unit of dq is like infinitesimal version of delta q, all right? And delta q is q final minus q initial. So when you subtract from q, all you get units is q. It's like rupees minus rupees is rupees. So you get the same, okay? So you get coulombs, millicoulombs for this, and dt is like delta t, and you get seconds for that. So this is millicoulombs per second. Milli, take it out, and so milli into coulombs per second, and so this is milliamperes. Okay, that's the first answer. Then the answer to this question is here. And now this, average current. Okay, for a change, instead of doing here, let me show you how to do this there. I think many of you know that this, its expanded version is the following. Limit delta t tending to 0, delta x by delta t. And what does this say? It says instantaneous velocity, look at this, concentrate here, is nothing but this calculation subject to this condition. Meaning, it is nothing but delta x by delta t, but delta t would be small to the limit, tending to 0, and do that same calculation but with this understanding. Okay? But what is delta x? Delta x is x final minus x initial, and this is x t final minus t initial. Alright? So, suppose I were to do this and find out the average velocity. Now, if you drop this promise, that should be your understanding. If you drop this promise and just do this, you are getting average. So, there is just this difference between average values and instantaneous values. Average value is delta, you know, you wait for finite time, and finite change finites over a period of time. That's average. Averages are over a period of time. Instantaneous is in infinitesimal, in the blink of an eye you do this calculation. Okay? So, अभी average चाहिए तो ये calculation करना है. तो मैं इसके पास जाऊंगा, इससे पूछूंगा भाई what is x final? Now x final means, since he wants between 1 second and 3 seconds, so writing in his language, I say x at 3 seconds minus x at 1 second divided by, this is of course 3 minus 1 is 2, and all I have to do is substitute 3 and 1, and so substituting 3 here, I get 54, and 8 is 62, minus 1 is 8, and I forgot what I got the first time, so let me do it again. I'll do it slightly better. x3 minus x1, this constant term would cancel. So all I have to do is, in this, substitute once 3, once 1, and subtract 1 from the other. So when I substitute 3, I get, later when I substitute 1, I get 3. So this cancels out, so I get 54. So this is 54 and this is 2. So the answer then is 27 meters per second. But this answer is 27, this is 27 not meters but millicoulombs per second, and so it becomes this. 1 to 3 seconds is this much, and does this seem reasonable? Always ask this question. Does the answer seem reasonable? To me, it seems very reasonable. You see, the current is not constant, but it is increasing with time. So if I straddle across 2 seconds, 2 seconds is here. This is 2 seconds. And this is 1 second. And this is 3 seconds. So यहाँ से यहाँ तक का average will be more than 2 if the current is increasing. And so it is more than 25. It is 27, seems reasonable. Such seems reasonable doesn't guarantee that it is correct. But if it were less, it is a guarantee that it is wrong. So it's a kind of check. Okay, so we did these few questions. Why did I pull this? Well, one, to tell you that you are not learning anything new. Two, to tell you that from the world of instantaneous velocity, you learnt that if I give you a x versus t graph and somebody asks you what is the instantaneous velocity at that place, then it is slope of that tangent. Okay, so v is slope of the tangent. So now I don't have to tell you that in qt graph, if somebody asks you what's the instantaneous current, it's the slope of the tangent. Without subscript, it means automatically means instantaneous current, just as that means instantaneous velocity. And of course, yes, there is another thing. Once again, the same graph, xt graph, and somebody says, what is the average velocity between this time and this time? So you reach over to the graph there and draw the join, and slope of this join is the average velocity. Incidentally, that is so because this represents delta x, this represents delta t, and tan theta, which is the slope of that join, is nothing but delta x by delta t, which is the average velocity. And similarly, we can have the following. What is the instantaneous current between this point of time and this point of time? Here on the x-axis is t, on the y-axis is q. Okay, it seems there's a lot of clutter. What is old should go. All that is okay. So इस टाइम t1 और t2 के बीच में, instant t1 और t2 के बीच में, what is the average current? All you have to do is reach out there to the graph and here draw the join, check the slope. If you want the work all over again, you say this represents delta q and this represents delta t, and tan of this angle is delta q by delta t, which is nothing but, on the one hand, tan of theta is the slope, and on the other hand, delta q by delta t is the average current. So slope represents I average. And more such questions can be discussed. But the thing is, you can make your life a little easier by, thinking in terms of what you learned. I can pull these tricks in almost anywhere in physics. For example, I can say a particle is moving in one dimension along a straight line, and its momentum, its momentum is given by this graph. What is the instantaneous force acting on the particle at this instant? Now, force is given by dp by dt. So, it's the slope of this force, instantaneous force. And somebody says, what is the average force sorry, this is T. What is the average force between this instant and this instant of time? So I reach out to the graph, I draw the join, and I say slope of this join is F average. And I can just give hundreds of such examples, okay? So you don't have to learn these things again and again. You learnt it once in motion in one dimension, and so be confident, happy, and complete with knowledge in all such situations. Okay. Next is this. That's a long insulated wire. There is charge deposited on it, over it, with uniform density of charge lambda. And somebody grabs hold of this and is moving it with constant velocity v. Or rather, at the instant the velocity is v. What is the current? Will there be current? Now, for the first timers, we often are hit with the impossibility of the idea of current. हम कहते हैं भाई current हो कैसे सकती है, वो तो नॉन कंडक्टिंग चीज़ है, उसमें करंट कैसे हो सकती है? Well, current is the rate at which charge is flowing. It doesn't matter कि वो individually electrons ऐसे जा रहे हैं या physically पकड़ के तुम ले जा रहे हो, तुम ऐसे तुम force लगा रहे हो या electric field force लगा रही है, उससे फर्क नहीं है. The point is, if you stand as guard here, then do some charges go past that check post? दिखाई दे रहा है? हाँ, मुझे दिखाई दे रहा है, क्योंकि अगर मैं dt टाइम के लिए वेट करूंगा तो जो ये पार्ट है, लेट मी शो यू दिस मच ऑफ, यू नो, दिस पोर्शन, इट्स लेंथ इज v dt. Okay, this is the distance which the wire would travel by in next dt time, traveling with the speed v. So it will move forward with v dt. As it moves forward, ये जो point है ना वायर का, वो यहाँ पे पहुँच जाएगा. Next diagram I show you here. थोड़ा थोड़ा आगे बढ़ जाएगा सब कुछ, और ये रेड वाला जो है वो यहाँ आ जाएगा और ऐसे हो जाएगा, ये v dt वाली लेंथ यहाँ पे आ जाएगी. So what happens is, as it is moving, I begin to keep track of, I keep an eye over v dt length and I see dt time later. Second diagram is drawn dt time later, और ये जो ये वाला पीछे का हिस्सा है ना, ये चल के इतनी दूरी से चल के आगे आ गया, यहाँ पे आ गया, और जो फ्रंट एंड था वो उतना ही आगे निकल गया v dt. तो इसके अंदर चार्ज कितना है? आंसर इज चार्ज इज लैम्डा v dt, और वो सारा का सारा चार्ज अपनी चेक पोस्ट से देखे इस पिक्चर में आगे निकल गया. सो हाउ मच चार्ज फ्लू बाय लैम्डा v dt? And this charge flew by, now this incidentally is nothing but dq, the charge that flows in time dt, and you have to divide it by dt to get the instantaneous current. So divide this by dt and this cancels, and so you get lambda v for your answer. So in this situation, the current I is lambda v. Two more questions in this setting. This time I have a strip. I don't have a, wire, but I have a strip. The strip is infinite in length. And the strip is moving with velocity v. And this is an insulated strip of insulated, of non-conducting material, and charge per unit area. ये area है इसमें, उसमें length था, तो charge was per unit length. This time charge is per unit area, and the width of this strip, this is b. What is the current? Once again, we stand as guard here at the check post and we'll want to know how much is the current. Either you can do like this, or let me first give you a third question. In this third question, we have this, that is, the charge is in entire volume. It's not on a strip, it's not on a plane. Here it was on a line, here on a plane, here in a volume. And in the entire volume, the charge is uniformly distributed and the density is rho. And या तो मैं इसका radius दे सकता हूँ या area A declared है. So now this is also infinite. And this thing is also moving with velocity v. This time also the question is, what is the current? The answer to all these questions is lambda v. Lambda v. Just like to the first question, it was I is equal to lambda v. You say, but sir, no, this is the answer to the second question, and let me write it close to the second question, lambda v. That's the answer. So you say, but what is lambda? There is sigma here. Well, you just collapse it into that situation. And so what is the charge per unit length? Well, if you take 1 unit length here, like this, 1 unit length, then whatever is the charge within this is 1 unit length, and the width is b. So the area of this is b into 1, and so the charge on this is b into 1 into sigma. That collapses and becomes like this black line, like that. So all the charge comes from here to here in the darkened portion. And so on that line of charge, what is the charge per unit length? All the charge comes here, and so this is the charge per unit length. So you substitute this for lambda, and so you get the answer as b sigma v. You do the same thing here. To determine the lambda for this situation, you take, if you collapse it, how much charge will come on 1 unit length of that wire? That charge is the one which is presently sitting in 1 unit length of this cylindrical space. So this is 1 unit. So the volume of this is 1 into area is A, into rho. Charge is stuffed everywhere inside this. Volume density of charge rho. So this much of charge, it collapses in and makes itself available in that style in 1 unit length. So this is nothing but lambda. Substitute it there and we walk away with the answer to the third question. So the answer is rho A V. That A could also have been pi r square. Had I given instead of this the area, the radius of this as r, in which case A would be pi r square. Okay, so we just finished 3 questions, and we'll resume. We have more things to do. We'll resume very shortly. Thank you. The next thing that we'll be doing is discussing what is known as current density. Current density, the symbol used for current density is J. Current density J, as you can see, is a vector. So it has got 2 aspects, direction and magnitude. First, let's talk about direction. So its direction is direction of J is direction of conventional current. magnitude of J, that is J is defined as I by S. Now, for this definition to be working, I must be uniformly distributed over the entire area S, and secondly, area S must be perpendicular to current. Now, what is all this? It's the following. Imagine something like this. Wire. I have shown you cylindrical wire, circular wire, and I am showing you a magnified view of this. Current I goes through this. Now, if this area is S, or which is the same, this area, then the current goes penetrating through this area here. The charges, current is made of, these charges flying by. So a blizzard of charges go that way and they go penetrating the area S. And the total current is I. So what is J? Since, now I imagine that in this situation, current is uniformly distributed. That is, charges are not, densely packed in one area and sparsely, packed in another, but they are uniformly packed over the entire area S. Then in that case, J would be I by S, because the first condition is valid because they are uniformly distributed, the current, and the second, this area is like this, whereas the current is going like this. So it is penetrating orthogonally, and so this calculation would do the job. As an example, if the current is, say, 12 amperes, and if this area S is 4 centimeters squared, then J would be 12 amperes divided by 4 centimeters square in this situation, and so the current density J would be, if you wish, you can give the SI unit, and so write this as meter square. So it would be 3 into 10 to the power 4. 3 comes from 12 by 4 and 10 to the power 4 by converting this into meter square. So ampere per meter square can also be written like this. So this is the SI unit for J, and the direction of J is the same as direction of conventional current, means in this diagram from left to right. So such a thing as this quantity called current density J. However, magnitude of J would not be this, but rather this. Now, from this we understand the following, that the current I would be given by J into S, provided S is perpendicular, but the current I would be given by J dot ds, J dot S, if J and S make some angle. In other words, it will be given by Js cos theta. And lastly, it would be given by J dot ds surface integral. The meaning of this is, this will be used, okay, let's begin with this. So there is this area, and J in this location is everywhere the same and uniform, and it is like this, and J, its magnitude is 5 ampere per meter square, and this is, say, 2 meter square. So what is the current through the designated area? Current I is given by this is 5 into 2, J into S, and so it is 5 into 2 is 10 amperes. Now an example for the second one. This time it's the same area, but just that J is like that. The current density vector is that way. And S, which is an area vector, is this way. This is the area vector. This is J vector. This is the angle theta between them. Suppose this angle is 30 degrees. And once again, S is given to be, say, 2 meters square, whereas the magnitude of J is, say, 6 ampere per meter square. What current penetrates through that area? So this time the answer would be I is equal to J dot S, which is Js cos theta, which is, substituting the values, J is 6, S is 2, and cos of 30 degrees is root 3 by 2, so you get 6 root 3 amperes is the current. And lastly, you could have a situation like this. We'll not do any computation here, just conceptually show you this last one working. So this time the charges are, not going nicely parallel to each other, and so the J is not uniform, but it is a non-uniform thing like this. And the area is also not nice, a planar area like this, but maybe the area is something like this. Something like this, okay? And you want to find out what current penetrates through this. So some of the charges are missing our area. This is an imaginary area and somebody wants to know what is the current penetrating. Now the last one is valid for this situation, and what you need to do, this is the most general one. Of this is the special case, and of this is the special case. So what you are supposed to do is, this calculation says divide the area into little patches. For example, there is a patch here. At that patch, check the area vector. So area vector is that way, ds. Check the J vector. So J is that way, J. Carry out J dot ds. You get a little scalar value out of that. And find out and take this area patch and check out area vector. It's that way. And J vector, it's that way. So take this J dot ds, once again a little scalar value. So this J dot ds tells you how many coulombs of charge go penetrating through that, and through this, and through this, and through this. So every patch, and you add it all up. Now that is this addition, integration. So this is how you come to know the total current in coulombs that goes past this every second. So that is this last one. Okay. Okay, with that, what is the next thing that we'll want to discuss? So with the current density over, the next thing we'll want to get under control is the idea of drift velocity. Look, what happens, how the current flows in a conductor like this. So this is magnified view of a conducting wire, and current is flowing through it in this direction. Now let's look at individual charges. Well, first of all, why is current flowing through this? The answer is current is flowing because after connecting it like this, an electric field is set up inside, and that electric field generates, applies force on the charges, and that moves the charges. So this is why there is a current. Maybe we can look at that picture in a greater detail in a little while. But fine, that is why the current is this way. Now, suppose we do not connect this. Will there still be, okay, show it to you separately here. So this time we did not connect it. Are the charges still moving inside this? Those conduction electrons, are they still moving inside this? The answer is yes, they are moving, and they are moving with a tremendous velocity. How come? The answer is the electrons are moving like this. They are moving randomly like this. Overall, an electron on an average is not going anywhere. जैसे कि इस कमरे में हवा के जो पार्टिकल्स हैं, क्या वो इस समय चल रहे हैं? हाँ, वो चल रहे हैं. वो जिस वेलोसिटी से चल रहे हैं, that would be the more, the greater is the temperature, and that velocity is known as VRMS, root mean square velocity. Okay, averaged out value is known as VRMS. Different particles will be moving with different velocities, and they are all moving randomly. So इसलिए वो हवा के particles overall, on the whole, they are not going anywhere. They are here only. लेकिन क्योंकि वो इधर जाता है उधर जाता है, तो overall वो वहीं का वहीं रह रहे हैं. So this is how a random velocity and the particles are moving. So if you take a check post like this inside this, say here like this, तो जितने particles, जितना कूलम उधर जाता है, वो उतना ही इधर भी पेनिट्रेट कर जाता है, क्योंकि रैंडमली वो जितना उधर जा रहा है चार्ज उतना ही उधर, एंड सो देयर इज नो करंट थ्रू एनी क्रॉस सेक्शन. बट व्हेन यू कनेक्ट दिस, व्हाट हैपेंस इज, नो दिस वेलोसिटी इज बिकॉज ऑफ व्हाट? इट्स बिकॉज ऑफ द थर्मल एनर्जी. सो सुपरपोज्ड ऑन दैट थर्मल एनर्जी देयर इज द drift. That is because of the electric field, there is a general movement this way. So the charge might go something like this. ऐसे गया, फिर ऐसे आया, ऐसे गया, ऐसे गया. Randomly चल रहा है, but वो धीरे 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 आगे भी बढ़ने लगता है. Do you see? आगे चलता जा रहा है. So जितना वो चल रहा है, वो काफ़ी ज़्यादा चल रहा है if you add up all these lengths. Largely this, but अगर देखा जाए तो वो यहाँ से लेकर के यहाँ तक चला आया, और ये जो है कितनी देर में चला, डिवाइडेड बाय दिस डिस्टेंस डिवाइडेड बाय टाइम, इज व्हाट इज नोन एज ड्रिफ्ट वेलोसिटी. ओके, सो ड्रिफ्ट वेलोसिटी, उसकी वजह से वो ड्रिफ्ट करता हुआ जा रहा है. दिस ड्रिफ्ट वेलोसिटी इज ऑफन वेरी लिटिल, एंड इट इज दिस विच क्रिएट्स द करंट, नॉट दिस रैंडम थर्मल वेलोसिटी. ओके, we have the symbol Vd for drift velocity. In fact, for the purposes of seeing how much charge goes past, the random velocity has no role, and just the drift velocity has the role. So if you want to find out the current, it's okay to entertain such a picture in your mind. Show it to you here. कि वो यूनिफॉर्म वेलोसिटी ड्रिफ्ट वेलोसिटी से चलता जा रहा है, वी डी चार्जेस. सो इफ दिस एरिया इज से ए, देन व्हाट विल बी द करंट? सिंपल कंसिडरेशंस टेल अस द करंट वुड बी एन ए ई वी डी, वेयर एन इज द नंबर ऑफ कंडक्शन इलेक्ट्रॉन्स per unit volume, also known as density of number density of conduction electrons. A is the area of cross section, E is the magnitude of charge on the electron, and Vd is the drift velocity, this one with which they are moving. The thermal velocity you can ignore for this purpose. The real velocity, the real motion of the electron is actually a superposition of the random thermal velocity with a directed drift velocity. Okay, so this is what we wanted to arrive at, and we have discussed this concept and the value. The formula for drift velocity we now next thing is, as these electrons, they go, moving around, they bump into, why did this electron go like that? The answer is because there is material, in the material there are charges, so they apply force on the incoming electron and turn it that way. So the electron goes that way. So that means the electron is, if this material, particles of the material weren't there, then the electrons will find the going much easier. So the material puts a resistance in the path of the moving charges. Okay, so that's the concept of resistance. The material comes on the way and resists the charges from moving. So this concept has to be converted into a definition. What is the definition of resistance? So what is just a word till now and an idea or a concept, we'll make it concrete by agreeing to call a certain calculation as resistance, and that calculation we'll employ every time, and such a thing is known as definition of resistance. So here is definition of resistance. You take any object, it doesn't matter what that object is. That object can be this marker, that object can be my hand, this object can be a potato, or it can be like nice wire like conductors shown, like this in physics texts. It can be anything. If you want to know the resistance between here and here, then what you do is take a cell, connect it like this. Presumably there is no resistance in this path, and so whatever is the potential difference, EMF of the cell gets, there. So the potential, this is secondary. What is primary is what is the potential difference between these 2 points. Calling that by the name V. So this may be anything else, maybe E or whatever. The thing is, if the potential difference between these 2 points as a consequence of this arrangement is V, and then a current I goes flowing, how? That current can be measured here, because whatever goes here comes out from here, and inside maybe it goes as a shower of charges all around, and takes some roots and goes exiting from that place like this. Okay, so something like this, and the charges all drain out from there and come from here and go like this. So the current can be measured there or it can be measured here. Then V by I calculation, we call it as the resistance of that object between these 2 points. If these 2 points are A and B, then it is the resistance of that object between points A and B. If instead these 2 lead wires were connected elsewhere, for example, from here I bend the wire and connect it there instead, A dash, and this wire comes here, B dash, then the current will, the charges will come out from here, spread all around and be collected and go like that. The current would now change and the resistance would therefore change, because if I have used, suppose it's the same potential difference, then current having changed, the resistance would change. So the resistance, there's nothing like resistance of an object. There is only a thing like resistance of an object between 2 certain points. Okay. Similarly, that object could be something like this. This is a symbol we use for resistor. So that object could be, that is making that idea, come alive in terms of the normal, physics in the texts. Let's call this point as A in this circuit, this point as B, and this point as C. If somebody says, okay, call this as R1, R2, R3. Somebody says, how much is RAB? The meaning of this is, the following. If you connect potential difference between these 2 points like this, then if the potential difference connected is V, then what current I goes? Now can you see, as that current comes in here, it splits into 2 paths. From here it comes like this and goes up and takes that route and gets out. And here it takes this route and gets out. So as it does that, whatever current goes through R1 also goes through R2, and so R1 and R2 are in series, whereas R3 is in parallel with the combined value of R1 and R2. Okay, so that how will you calculate that? So whatever overall resistance comes in the path, it can be computed by doing this. RAB will be V by I, where V is the potential difference you applied and I is the current that will be flowing in here, which is also, you can check it out here if you wish. But knowing in terms of series parallel, you can see what the answer would be. It would be this and this in series and this in parallel. Okay, you can think of what that computation would give you. You can even use some numerical values. But suppose somebody instead asked us what is RAC? Then conceptually what you have to do is not connect this other end of the wire here, but connect it here like this. Now the current would be delivered there, then it will take whatever routes and it will come out from there. So can you see, the current which will come this way will go via this, and so now this and this become in series, and that as treated as a single resistor is in parallel with R1, and now this will give you a different answer. So the resistance changes. So that bears that idea which we were talking about in general. So there is a thing like resistance. There is nothing like resistance of a network. There is only a thing like resistance of a network between 2 selected points. Okay? Okay, so that is the definition of resistance. Simple. क्या करना है? 2 पॉइंट्स के बीच में जहां पर रेजिस्टेंस हो उसको आप उन 2 पॉइंट्स के बीच में पोटेंशियल डिफरेंस V लगाइए, चेक आउट द करंट क्या जाता है, और V by I, उस कैलकुलेशन को अपन बोलते हैं रेजिस्टेंस बिटवीन दोज 2 पॉइंट्स ऑफ दैट network or object or whatever. Now what should be the units of it? Obviously units would be volt per ampere. Now this is given a new name and is called as ohm, OHM, and this symbol is also used. Okay. Next we'll want to define resistivity. Resistance is what is known as an extensive property, but resistivity is what is called as intensive property. So now resistance is over here and our new heading is resistivity. Resistivity is a property of the material and it changes from material to material. How is it defined? Resistivity is defined as it is defined as E by J. To understand this, the meaning of this, suppose we have this conductor and current is flowing through it. I need not repeat. All of us know why this current is flowing through it. Current is flowing means charges are moving. Why are charges moving? Well, because somebody must have connected something like this, a cell, and so that creates an electric field. It establishes an electric field inside that conductor. That electric field latches on to the loose conduction electrons and moves them. So the charges move. So as the charges move, now instead of talking about electrons which are negatively charged, all of us know that it is more convenient to talk about in such situations hypothetical positive charges. मतलब इलेक्ट्रॉन्स इस सिचुएशन में इधर मूव करेंगे, लेकिन हम पॉजिटिव चार्जेस को इधर सोच लेते हैं कि इधर मूव कर रहे हैं, ऐसे. So this is a positive charge which is moving this way. Now, so this is what is known as direction of conventional current. So इस जगह पे J इधर होगा और इलेक्ट्रिक फील्ड भी इधर ही होगी, और so जो भी इलेक्ट्रिक फील्ड है उस जगह पे उसका मैग्नीट्यूड लीजिए और J से डिवाइड कीजिए, तो ये उस जगह का, लोकल जगह का रेजिस्टिविटी हमें बता देगा. Okay, so this is the definition of resistivity. Now, using this definition of resistivity and this definition of resistance, we can maybe establish a result of this kind for a simple situation. आगे बढ़ने के पहले एक चीज आपको मैं और भी बता सकता हूं कि इसको, रिजल्ट को हम ऐसे भी लिख सकते हैं, J is equal to, with the arrows, E by rho. This information here is something extra to this. It, apart from whatever is the information here, यहाँ पे जो extra है, that is because of the direction, and it merely claims that J at a place will be in the same direction as E vector. मतलब लोकली जहां पे जिधर भी इलेक्ट्रिक फील्ड होगी, लोकल करंट उधर ही चलेगी, चार्जेस उधर ही मूव करेंगे. दिस इज व्हाट दिस इज सेइंग. नाउ वी विल लेट्स कंसिडर द फॉलोइंग. दिस इज अ uniform conductor, and the resistivity, what are the units of resistivity? Its unit should be Newton per coulomb. This is Newton per coulomb, and J is current, ampere per meter square. So meter square jumps there. Electric field is Newton per coulomb and J is ampere per meter square. So ये आ गया. Now this ampere is coulomb per second. So you can, write it in other forms, and so that is what it is. Something like, if you, this is Newton, if you wish you can write it as meter per second square, and this is coulomb per second, so 1 per second cancels out and 1 per second stays, so you have coulomb square per second between these two, and a meter from here, and this gives you meter cube, and there is kg also from there, and so that. So this stuff, we can give it another name, or shortly we'll see another way of writing the units. The units of something can be written in SI system. If you want to write the units, there would be several ways. In fact, for that matter, in any system there would be several ways of talking about the same thing, because there will be several formulas connecting a quantity with other quantities, and it's because we have been naming all the quantities and calling those units, so we have different combinations ending up with the same value. All right, so here let's consider the following situation. This is a conductor of length L, and I wish to find out its resistance. Its material is such that its resistivity is rho. The area of cross section is A, and it's the same throughout. Now, to find the resistance, the definition let us use, I have to connect it by using a cell whose potential is V, and then I want to find out how much is the current I. Okay, once I get that, then resistance would be V by I. Now, if the potential difference is V, there would be if there is electric field E, then V is EL, ED formula in action. So it is, so potential difference is EL, and current I written in terms of J. If the current density is called as J, then current I would be J into A. J into A. Substitute V and I over there. So I get R is, for V I write EL, and for I write J into A. But E by J is same thing as rho. So I replace this combination E by J with rho. So I get R is equal to rho L by A. Okay. A formula which is familiar to more students than this formula. Now this formula incidentally can also be written in this form. J is equal to, E stays as E, but 1 upon rho, 1 upon resistivity is called as conductivity, and we'll use symbol sigma for it. So this is conductivity. Conductivity sigma is 1 upon resistivity rho. So this and this, they are the same. Incidentally, this is the definition of resistance, and Ohm's law is that if you, the one way of saying what is Ohm's law is that the graph between potential difference V versus the resistance I is a linear graph. That's Ohm's law. Written in mathematical form, we'll say V is proportional to I, or I is proportional to V. If you double the V, this becomes double. Now, this Ohm's law is valid only for certain materials, and for the materials for which it is valid over a certain range of potential differences applied. For the materials for which it is not valid, they are called as non-ohmic, and the ones where it is valid, they are called as ohmic. So all the V versus I graphs for all the materials won't be like this. They could be like this. This is non-ohmic. This is not following Ohm's law, whereas this is ohmic resistor. You can notice that if it is proportional, and if I write the proportionality constant as R, then I can write V is equal to IR. So this, the definition, and this Ohm's law, are they the same, or is there some difference between the two? Yes, there is a difference. You see, Ohm's law says this R remains constant, whereas this definition makes no such claim. So even here, the definition of resistance is valid. It is V by I. It's just that the resistance changes. For example, for this VI graph, what is the resistance when the current is so much? Now let me find out how much is V. V is this height and I is this. So this height, the red one, divided by this one is how much? Well, it is tan of this angle. So that is the resistance. But if you go to this level of current, then a similar thing would be tan of this, and the resistance has increased. So the resistance is changing from level of current to level of current, or level of voltage to level of voltage. So this is not following Ohm's law. Ohm's law says V is equal to IR and R remains constant, in other words. Similarly, This is also Ohm's law, J is equal to sigma E, but with the insistence that sigma remains constant. This is then known as, that is, the conductivity remains constant. But there will be materials, for example, the one for which this is the graph whose resistance is increasing, means resistivity is increasing, means conductivity is decreasing, and sigma is not constant. Now, if sigma is constant, then this same thing will be called as Ohm's law in point form, or local Ohm's law for a point, and this is Ohm's law for the cross. Okay. A little work on R is equal to rho L by A. We have a cuboid. This is A, this is B dimension, and this length dimension is C. Now, what is the current resistance between these two, left and right? R, resistivity of the material is rho. So, R left right is equal to, formula to be employed is rho L by A. However, you please remember one thing, L is that direction in which the current is moving. L is that dimension. So, here L is C. So, we have rho L by A. A is the area, this area that is comprising of the other two dimensions. So it is AB. So that's the answer. But suppose somebody wanted R bottom top. Then it means he is connecting here to the bottom, the wire, and current will be tapped from there. So current enters here and goes like that. It spreads and goes out. So that resistance would be different, as you know, and now it will be rho L. L is this dimension, that is B, and the remaining two come here, C and A. So you see the resistances are different. Okay, now let's look at another question. In this question, we have the radius of this is A, the radius of this is B, the length of this is L. And this is, show you maybe a three-dimensional diagram of this. This object is a frustum of a cone like this. Okay? And one last thing, the angle at which this is increasing is very small. So I can speak of that by saying B minus A is the difference, and that compared with L is much greater than that. And so B minus A by L is much less than 1. That is given, and the density is rho. And we want to know the resistance, okay? Call this as A and this as B. These represent the lead wires, and we want RAB. This question would be handled in this manner. Show it to you in this 3D picture of the same thing. We slice it up into okay, maybe before I can do that for you conveniently, what I need to tell you is we'll work with here first. It is the following. So we suspend that, and we are now discussing series and parallel, resistors in series and parallel. First, series. So So here are two resistors R1 and R2 and they are in series. Now call this point as A, call this as B, and I want to know RAB कितना है. इसको कुछ लोग effective resistance भी बोलते हैं, R effective कितना है between points A and B. The answer to this is, it is R1 plus R2. Now they are called as being in series when whatever current goes through this is the current through this. So the current is the same, but the potential difference across this, think Ohm's law, it is IR1 and that is IR2, and so the potential differences are different. Call this IR1 calculation by the name V1 and this as by the name V2. So the potential difference are different. So in series, the hallmark of series is current is the same, potential difference may be different, but may be same, but may be different. There is no restriction on that. But the further thing is the sum of these two potential differences is the overall potential difference. I want you to tie this up with, check out the previous video on capacitance, and there also we had this business of series and parallel. So if you did not get something very nicely there, then check this and look at that again and you will see a similar discussion going on there. So here the currents don't add up. We don't say what is the net current. There for series the charge did not add up. Here the currents don't add up. We just say current is I. Okay? But the potential differences add, and that common current doesn't add up. So if somebody, okay, that's series. And parallel is a situation like this, R1, R2, which can be replaced with an equivalent. That is, if you were to call this as A and B, then RAB would be given by the formula 1 upon R1 plus 1 upon R2. If there are more of them, you can add more. That is, if there are more resistors here, you can add more terms. So that gives you the... Now, here, whatever is the potential difference between here and here, now this is common up to here, and this comes here. So potential difference across this is the same as this, which is also across this. So the potential difference across this, call it as V, and this is also V. It's the same. Now potential difference being same, let's apply Ohm's law. Just as we used to write C is equal to Q by V every time there, we can also write V is equal to IR every time here on this side. And now we can see out of three things, if any two are known, the third can be known. So for this resistor, I know two things, the potential difference and resistance. So I can find out the current. Calling that by the name I1, can you see that I1 is V by R1, whereas I2 here is V by R2. The currents are different. So here the currents may be different, but the potential difference across them is same. And if somebody asks you, what's the potential difference across these two put together? Then potential differences don't add. But if somebody says, through this, in this box, how much current is going? This. Then that current adds. So net current going into that circuit is I1 plus I2. Currents add, potential differences don't. Okay, match this idea up with a similar discussion in capacitors. And maybe since you understand this, since it is more intuitively more clear, maybe something that wasn't clear there would now become clear to you as you look back at it again. Okay, so we have to solve this. Now to solve this, what we will do is we chop it up into such thin slices. We imagine it chopped into such thin slices, many of them. For each slice, we can use the formula rho L by A for getting its resistance. And then we do see that whatever current goes penetrating through this, later उससे जाता है, फिर देर सवेर इससे भी निकलेगा. So these things are in series. And so we can use, add all this up. So इस चीज़ को हमें implement करना है. Now I come back here. For this rho L by A के लिए मुझे इसका एरिया चाहिए हर जगह पे. So I do this by doing something like this. I say, let me go a distance x down the line from here and let me find out what's the radius there. To find that radius, one simple way is to use unitary method. देखिए इसी लाइन पर आगे आगे चलते जाइए तो जो रेडियस शुरू में a था वो ग्रो करता करता b बन गया. तो L दूरी ऐसे जाने पर रेडियस कितने से बढ़ गया? वो बढ़ गया b माइनस a से बढ़ गया. L दूरी जाने पे, एक यूनिट दूरी आगे बढ़ने पे इतने से बढ़ा. सो x यूनिट जाने पर इतने से रेडियस बढ़ेगा. Now that's not the radius, this is the amount by which it would increase. So how much is the radius? It is a plus this. So that is the radius at that place. Why do I want the radius? Okay, let's first get it and then we'll see. So LCM is ऐसे ही रहने दीजिए. Now I want the radius for this reason. Come back to this picture. Rho L by A लगाना है तो उसके लिए एरिया में नीचे I have to do pi r square to the radius, and so this radius r which we found out there will be employed in doing pi r square. So now what is the resistance of this disk? I'll write it here. So resistance of this disk is rho, I guess I have to change the marker, rho L. L is that dimension in which the current is traveling, which here is, so we say the disk which is at a distance x and within the next dx, ye wala. So L is dx. So rho L by A. A is pi r as copied from here, A plus B minus A by L x whole square, rho L by A. And now this represents the resistance of this. Just change x and make it that, and it gives you that resistance of this disk. So in सबको change करते हुए सबको add कर दीजिए from x is equal to 0 from beginning to end. X is equal to 0 to x is equal to L. That gives us the resistance between the 2 points A and B, and that will give us the answer. Now integration of this is fairly simple. Rho and pi being constants, take a walk out, and this, its integral will work somewhat in the style of 1 upon x square, which is x to the power minus 2, integral of which is minus 2 n x to the power n minus 1. So नीचे minus 3 आ जाएगा. Meaning this becomes A plus B minus A upon L x and by chain rule I have to multiply by the derivative of this, which is B minus A by L. And the limits 0 to L. The minus sign can be taken care of by flipping the limits. So I get rho by pi, B minus A by L, this is this part, and 2, and now the limits. First we substitute, to take care of minus sign, flip the limits. First we substitute 0. So I get this. And then I substitute L for X. So L cancels out and I get 1 upon B. I do not miss out on a little something. This can be written as 2 rho by pi B minus A upon L LCM A cube B cube, and up there we get B cube minus A cube. Well, I'm not so convinced about what is going on. So what I'll do is make a check. The check would be dimensional check first. So this is, its structure should be rho L by A. Now this is rho. This is dimensionless. This is definitely not L by A. L by A is supposed to be 1 upon length, and this is 1 upon length cube. So already there is some problem here. Now if we see this is of the structure rho, this is L, and this is like A. Length is square. So this is fine. Oh. First thing is these are the limits and they have to go there, 0 to L. Secondly, okay, I check the dimensions here. So this is rho, this is dimensionless, this is definitely not A because it is volume. So no, that is not okay. So between here and here I have already made a mistake. So I check the differentiation again. Rho by pi goes out and oh, it's not differentiation, sorry. So that was a pretty silly mistake. It is, I'm supposed to be integrating and not differentiating. It's this sign of integral and I'm differentiating. So okay, finally, whatever, silly or not silly, I've caught my mistake and I'll correct that. So I have to integrate this. Rho by pi goes out and integral of this. Now this is like 1 upon x squares integral. These kind of integrals, simple integrals, we can do by guesswork. So can you guess that whose integral is this? Oh, that is minus 1 upon x. Or as a first guess, I'll take it as 1 upon x. So as a first guess, the integral is 1 upon, I guess I should take another black marker. So अभी ये रो बाय पाई आ गया और इसका एज अ गेस वर्क आई गेस इट टू बी a plus b minus a by L into x. Now watch how I handle that kind of an integral. So that is my guess and I reserve the right to tweak it somewhat. The idea is this is integral of that, provided upon differentiating this I can get that. So I'll differentiate it and see what I get. So when I differentiate, I get all this because this is of the structure 1 upon x, and so derivative would be, this is x to the power minus 1, derivative would be minus 1 x to the power minus 2. I'll get all this, but in addition I'll get b minus a by L. To neutralize that, I'll multiply by L minus b by a. Okay, and there is of course a minus sign which I'll employ for flipping the limits. So I get x is equal to L to x is equal to 0. Then rho pi, this L upon b minus a, and now first we substitute x is equal to 0. So I get 1 upon A. Then I substitute x is equal to L. L cancels. Thereafter A and A cancels. So minus 1 upon B. I'm quite happy to note that this is a positive calculation because 1 upon A is bigger than 1 upon B. A being is smaller, and so this is greater, and so this is positive. This also is positive, denominator here, and everything else is positive. So we are getting a positive answer. That's how as it should have been, pi L B minus A, and then I see B minus A up there divided by AB. This cancels, and our final answer is rho L upon pi AB. This is indeed of dimensions rho L by area, meter square. And finally, there's another check. If both A and B are equal, say both are equal to R, then I find it is what is written here is rho L by pi R square, and the shape becomes cylindrical, and pi R square is A, and we come back to the same formula. So it checks. Okay, so that is done. Now what is I'll want you to know the following. The resistivity of a material changes and increases with increase in temperature. For many materials, it increases with increase in temperature. The increase in resistivity is given by rho 0 alpha delta T. The new resistivity, rho, is given by to the old resistivity at the change. So what do you get? You get rho 0 into 1 plus alpha delta T. This alpha, this is of the same, this equation and this equation is somewhat like thermal expansion, only this is known as, there it is known as coefficient of linear expansion, and here it is known as coefficient of resistivity. Its units would be something like per degree Celsius or per Kelvin. And somehow we managed to sidetrack the issue of what is the unit of resistivity. Now if we use the formula R is equal to rho L by A, immediately we know the units of resistivity. Keep resistivity here, this, and everything onto the other side. A clash between this and this leaves us with a meter down here. And when it goes there, along with the ohm, so the units become ohm meter. Okay, you can also write it as ohm meter. So those are the units of resistivity. If you have a resistor and you of resistance R and you apply a potential difference V across, then as the current is driven this way, the charges, they bump into the material and heat is generated, because as they bump into the material applies force on them, and the material particles themselves are left jarring and oscillating, and this random, so the lattice atoms go oscillating, and this means that is what is known as heat. So heat is generated. That the rate at which heat is generated is known as power dissipated as heat. So power dissipated as heat in a situation like this calling it by the symbol P, it is given by V square by R, and the following forms are also available because V is IR. So if you replace the V there with this, then I have I square R, or If you replace just one V with this and leave the other V, then we have V into I. Okay, so these three forms for power dissipated as heat. If somebody asks you how much heat is dissipated, now it all depends upon whether P is constant of time or P is variable. If P is constant, if you look at this, when will P be constant? When the current is constant and the resistance also doesn't change with time. Is it possible that the current is constant and resistance is changing? Yes. If the current is constant, the resistor gets heated up, and because of the increasing temperature, the resistance could change. Also, the current itself could change. For example, it could be AC. So, for whatever reason, if P is variable, we'll discuss how we compute the heat generated over a time if P is variable. But if P is constant, all we need to do is heat generated Q. What is this? This is heat generated over a time T will be given by P into T. Whereas here, this Q, the heat generated over time T, would be given by P dt integral T is equal to 0 to T is equal to T. That is, this would be given by V square by R into T or V into I into T or I square RT. Whereas here it would be given by Vi dt integral 0 to T or V square by R dt integral 0 to T or I square R dt integral 0 to T. Okay. Another thing is, this result you should know, the resistivity is given by M N E square tau. In this is the resistivity of the material. This is mass of an electron This is magnitude of charge on electron. This is number density of conduction electrons. And this is what is known as relaxation time. Relaxation time is the average time between two successive collisions, average taken over a substantial amount of time, that is over many collisions, and computed for many electrons. This formula tells us that if you increase the temperature, the resistivity of a conductor will increase. It will increase because relaxation time tau will go down upon increasing the temperature. So as you increase temperature, increasing temperature decreases tau, the relaxation time, thereby increasing resistivity. Now, this is valid decreases tau, I must insert here, for a conductor. Whereas for a semiconductor, the story is a little different. So what happens as resistivity is increased? This increases R, implies R increases, resistance also increases. But for a semiconductor, here is the story. Increased temperature, if you increase temperature, what happens? N increases. That is, there are more holes and conduction electrons in the conduction band created, because through the energy barrier, across the energy barrier, more electrons will have enough energy to clear that energy barrier, energy gap. And so as they clear the energy gap, there are more conduction electrons in the conduction band, as well as there are more holes in the valence band. So this doubly, goes to increase N, the number density N increases. Now as N increases, a consequence of this is that, as you can see here, others remaining more or less the same, the rho decreases. This will result in decrease of resistance. So upon increasing temperature, increased temperature, resistance of a semiconductor decreases. Increased temperature, resistance of a conductor increases. So they go the other way. Opposite way of each other. Okay, next would be Kirchhoff's laws. There are two laws. They have names. The first law is called as junction rule. The second one is known as loop rule or voltage law. Junction rule is based on law of conservation of charge. Whereas this one is based on law of conservation of energy. Junction rule says, talks in terms of what we call as junction. What is a junction? A junction is a join is a thing like this. It is so here is a junction where three or more wires meet is called as junction. The law says the currents coming in at the junction, sum of the currents coming in at the junction is equal to the sum of the currents leaving the junction. So if this is I1, this is I2, this is I3, then as per the junction rule, we have I1 is equal to I2 plus I3. Now there could be more things, there could be this, then this plus this would be equal to that plus that. Sum of the currents entering the junction is equal to sum of the currents leaving the junction. An example of this is this question. So this is 5 amperes, this is 2 amperes, and 3 amperes goes out, 4 amperes comes in. How much goes this way? What current comes here? तो हम सारा हिसाब लगा लेते हैं. 5 आया और 2 और आया, सो इस जगह पे 7 आया. 7 में से 3 इधर निकल गया, तो आगे इस जगह पे 4 आया, 4 एम्पियर. Another 4 joins in, and so this must be 8 ampere. Answer. Loop rule. Loop rule says the following. It says, in a closed loop, the algebraic sum of potential differences across various elements in a circuit equals 0. So what does all this mean? It means the following. The loop rule is best demonstrated by solving a full-fledged problem. So I'll do that. Let's call this as R1, R2, E1, E2, R3, and this is E3. All the values are given to you. You can think numbers in place of these. The job on hand is to find out the current through each branch. Incidentally, once you know the current through each branch, several other things worth finding out you could be quizzed on them. For example, if you know the current in this upper branch, you could be asked at what rate heat is being dissipated in this resistor. Now that is the power dissipated. So it will be whatever I you find out, I square R2. Okay. Or we can say at what rate is this cell, this battery absorbing energy. Now if the current is going that way, it is absorbing energy. It is converting that electrical energy into chemical energy. On the other hand, if the current is this way, it is releasing energy. So we can say at what rate is this releasing energy in that event. Or we could ask questions like, what is the potential difference between these 2 points, any 2 selected points? Now all of this can be done provided we can first of all, come to know the current in each and every branch. So first thing is to learn how to do that. To do this, we call the current anywhere by any name, such as here we call it by the name I. Let the current be I. We don't know the value of I. We just call it as I, and we'll set up some equations and solve them and get the value of I. So presently we proceed by calling it as I. अब उसमें से जो करंट आया, इधर कितना जा रहा है मुझे पता नहीं है, तो उसके लिए भी एक कोई नाम दे देता हूं. सो आई कॉल इट एज I1. ठीक, तो फिर इधर कितना जा रहा है? Now you can use Kirchhoff's first law. So out of I1 goes this way, so the balance I minus I1 must be going this way. Then this I1 and I minus I1 come together, merge together and become I again. So this is I again. Okay, and this I comes like this and goes that way. Fine. Now, what is Kirchhoff's loop rule? And how many unknowns have I introduced in my problem? I have introduced 2 unknowns. Kirchhoff's loop rule, as the name suggests, it would be applied, it is applicable over a closed loop. I can see at least 3 different closed loops here. One is this. Start here, go like this, come back. Closed loop. The second is, let's say start here, go through the lower branch, come back. Third is start here, go through the upper branch, come back. these three equations for three loops, for each of them employing loop rule. I am about to explain to you what this is, but employing loop rule, we'll get an equation. So we'll get three equations, but there are only two unknowns. They are I and I1. Well, it just means that the three equations are not independent. That is, in other words, any two equations you decide, unko manipulate karoge, mix them around, something like first equation plus second equation, or first minus second, or anything like that, and they will result in the third equation. So the third equation is not a separate stand-alone information. That information is coming out from the first two. Any two give you the third. So we, in such a situation, mathematicians say there are only two independent equations. So they are as good as two equations, and they'll enable you to get two unknowns. In other words, we need to select out of the three available, we select any two loops and we write the equation coming out of the loop rule, and then we solve the equations. Okay, so what is loop rule? Say it again. It says algebraic sum of potential differences across various elements in a closed loop equals 0. What is an element? Well, in this diagram, you are seeing two types of elements, the cells and the resistors. But to be sure, there can be other elements. There can be capacitor, there can be this, which is known as inductor. Its inductance, to come in later lectures, is measured in a unit, SI unit called Henry. This is in farads. This is in ohms, this is in volts. So these four things could in general be hanging around in your circuit. And so what you do is, you go in a loop, start somewhere here, and let me demonstrate for you how the loop rule will precipitate an equation. We'll go this way, although we can go the other way also. Both are equally okay. But I have to go some way, and to demonstrate, I have decided to go this way. Okay, so let's go this way. As you go from here to here, nothing is encountered. None of those four things is encountered. So you don't write anything. And then this is encountered. So I have to write something. Now what do I have to write? It says algebraic sum of potential differences across various elements. So what does the word algebraic here mean? It means that the potential difference, it could be written as positive or negative. So whatever is the potential difference across these 2 points, that has to be written. Suppose it is 20 volts, then I have to write 20. But one thing is not clear to me. Shall I write plus or minus? Okay, so there is this thing. So for each term, each element, a term has to be written, and the term will have two things. This and this. That is, it will have a sign, plus or minus, and it will have an amount, means value, magnitude. So we'll have, for example, here I could be writing something like plus 20 volts, then minus 30 volts, and like that. So plus, minus, you keep doing that for the entire loop, and then you set it equal to, so 20 volts plus 30 volts minus so many volts, and all that. Down the loop you go in a closed circuit is equal to 0. So this is the meaning of algebraic. Algebraic means this sign, and amount. Algebraic sum equals 0. Whatever. So this is negative because the term was negative, but I added them all up. Okay, so this becomes negative. So you just add them all up. Some terms are positive, others are negative. That's the meaning of algebraic sum. So how do I know which term is negative, what is positive, and how do I know amount, the value to be written? Okay. For the value to be written, for different elements, there is a different rule. And for the amount to be written, sign to be written, you just ask one question. You ask the following question. This is one way of doing it. You just say am I going up the potential ladder or am I going down the potential ladder? Okay, so let's start here. So I have to write some term. यहाँ से चालू किया, यहाँ तक आए, कुछ नहीं लिखना है. अब यहाँ से यहाँ जाता हूँ, कुछ लिखना है. तो वो जो लिखना है वो या तो प्लस होगा या माइनस, अभी डिसाइड करता हूँ. और उसका अमाउंट लिखना है. सो अमाउंट कैसे आएगा? वेल, ओम्स लॉ. So potential difference across this is given by Ohm's law. How much is it? It is I1 R2. V is equal to IR. That's the law here. So potential difference is I1 R2. Now shall I put a plus or minus? To settle that, always ask one question. Am I going down the potential ladder or up the potential ladder? The answer is, if you are going down, write minus. If you are going up, write plus. So am I going down? Well, you see, this current जो इससे चल रहा है, this is going in this direction, conventional current, because inside this the electric field is set up like this, in that same direction. Remember, J is equal to sigma E. Sigma is conductivity, a positive number. J is conventional current direction of current density, which is same as direction of conventional current. Now conventional current going that way, J must be that way. So if J is that way, so J is that way, and E therefore must be that way, same way. These two vectors must be in the same direction, this being a positive scalar. So electric field agar idhar hai, so as you know, it points from higher to lower potential. This must be higher, this must be lower. So I am going down the potential ladder. So I'll put a minus here alternately. Now, if in this same situation, if instead of traversing my loop like this, had I decided to traverse it like this, तो इन तीन को पार करने के बाद जो भी प्लस माइनस लिखा होता, यहाँ से जाते टाइम I will argue the same thing again. I'll say देखो भाई यहाँ पे करंट ऐसे जा रहा है और करंट ऐसे जाने का मतलब J उधर है, तो इससे क्लियर है कि E भी उधर है, तो ये हायर है ये लोअर है, लेकिन मैं ऐसे आ रहा हूं तो मैं लोअर से हायर जा रहा हूं, इसलिए मैं वहां पे आने पे प्लस लिखूंगा. ओके, अगर उल्टा आ रहा हूं, लेकिन अभी इधर जा रहा हूं तो माइनस. सो आप चाहें तो ऐसे आर्ग्यू कर लें और प्लस माइनस डिसाइड कर लें, चाहें तो ये याद रख लें कि मूविंग इन द डायरेक्शन ऑफ करंट यू राइट माइनस, थ्रू मूविंग इन द डायरेक्शन of the current going through a resistor you write minus, and moving opposite to the current as you traverse the loop going through a resistor you write a plus. Your choice. Okay, so we are going down the potential ladder, minus this. Here nobody has to tell you that you are going down the potential ladder, so I'll write minus. Rule is very clear, nothing is to be thought, and the amount is written right there, so minus E1. Ohms, यहाँ तो फिर भी Ohm's law लगाना पड़ा, यहाँ कुछ भी नहीं. Okay, then I come round like this. Now this current is going like this, so this must be higher, this must be lower. Okay, current is flow of positive charges, and positive charges are going that way. It means this must be higher potential and this must be lower potential. Okay, so I'm going like this, so I'm going from lower to higher potential, lower to higher. So I have to write plus. So plus, and the current amount Ohm's law से मिलेगा, so that is IR, and I is I minus I1 into R3. तो यहाँ तक लिख लिया. फिर ये, that is very simple, minus E2 is equal to 0. Let's practice it once more. This time I'll take the following loop. I'll start here, go like this through this branch, then come down, then go like that, फिर ऐसे जाके वापस ऐसे. So this is how I'm going. Okay, so let's start here. Nothing is written. फिर ये something has to be written. There is some element. Ohm's law will decide. So it is minus IR, IR1. फिर नीचे से आए, यहाँ पर you are going up the potential ladder. Negative से positive terminal higher potential पे जा रहे हो. Amount is written right there. So plus E2. Then this is going down the potential ladder. So minus by an amount IR, which is I minus I1 into R3. Notice that this same thing, when earlier we were traveling this way, it was plus, but now we are traveling this way and it is minus. This term and this term. Then idhar se aaye plus E3 is equal to 0. Now between these two equations, we have two unknowns. Their names are I1 and I. And the rest of them are numbers as given in a problem, such as E1, R2, R3, etc. And so with those numbers there, only these are the unknowns. We can solve these and get the value of I and I1. Once I get I and I1, then from I subtracting I1, I'll know this current. तो ये मिल जाएगा. I1 directly मिल गया, I भी मिल गया, तो मुझे हर ब्रांच में करंट मिल जाएगा. So this is the way how Kirchhoff's, this you now understand how loop rule works and how it is employed along with junction rule, the first rule of Kirchhoff, to do this sort of a work, which is known as analyzing a circuit. Okay. Maybe I should right away teach you this. Suppose at this place I had a capacitor. Let's say its capacitance is C. Then going through the upper loop, going through the lower loop, those same elements, same thing. But going through the upper loop, something would change, because that is also there, another element. And so let's see, where should this element come? As you come from here to here, you wrote minus this, and so I must insert a term here. Okay. So what will I write there if there is a capacitor? Look, this is current. Current is coming in and then it stops there. There is no further route for the charges to go. So if there is traffic and if the cars stop there, there will be a piling of charges there. So the charge here will not be constant but would be changing with time. That variable charge, I call it by the name Q1. The left one is positive, the positive charge, stream of positive, नदी आ रही है charges की और यहाँ नदी रुक गई है और वो बहते चला आ रहा है, तो इसका मतलब है यहाँ पर पानी बढ़ेगा. So this is variable value Q1 and it is increasing with time, and this is minus Q1. Okay. So, okay, as I go from here to here, whenever working with capacitors, always it's not a bad idea to write this somewhere on this side. So what is the potential difference? Well, write this in this form. V is equal to Q by C. It will immediately tell me what is the potential. This says out of 3, if you know any 2, you will get the third. I know 2 things about this capacitor, the charge on the capacitor and capacity of the capacitor. So I can get the potential difference. How much is it? It's Q by C. So in this case it is Q1 by C, but you are going from higher to lower potential. Is this higher potential and this lower? Indeed it is, because we have been taught that electric field goes from positive to negative charges, and we also have been taught that electric field goes from higher potential to lower. So this must be higher and this must be lower. So I'm going down the potential ladder. So I'll write minus and I'll write Q1 by C. That's what I'll write. And the rest of it goes like this. So I get this time round these 2 equations. But you see there is another thing, Q1, which is not known. So what do I do? Well, do you see this Q1 is nothing but this current I1 comes like this, and so if I ask you at what rate charges do you see the traffic of charges go by? You say so many coulombs per second, I1, so many, okay, current is I1, and here I1, so 7 vehicles per second, here 7 vehicles per second. So it is clear at the parking lot, vehicles must be increasing at the rate of 7 vehicles per second because they can't move any further charges. And so the rate at which Q1 or the vehicles parked there are increasing must be I1. So I write this. I am saying all this because if only the I1 were marked this way, then it would be decreasing Q1, and then this, in that event, I have to write I1 is minus dQ1 by dt. Okay. So if only this current were marked the other way by me, then I have to write this. But presently I have to write this. Were the current in the upper wire, okay, marked in the upper wire, marked leftwards, then I write this. Okay, so presently this is fine. Now I have three equations and I deal with them like this. I take I from this, compute it, and every occurrence of I here, जैसे ये है, इसको मिटाऊंगा और जो भी I की वैल्यू यहाँ से निकलेगी, please understand R1, E2, etc. are all numbers in a given problem. Only I is what I have introduced. So I की वैल्यू numbers के terms में निकाल के यहाँ डाल दूंगा. तो इस इक्वेशन में I की वैल्यू जो होगी वो नंबर और I1 के टर्म्स में होगी. तो यहाँ पर नंबर और I1 आने से ये सब कुछ यहाँ पर I1 होगा. वो हर I1 की जगह मैं dq by dt डाल दूंगा. सॉरी, dq1 by dt. Okay, and then there is this. Now for those of us who have maths, we can say, oh, that's a differential equation, and I can solve that differential equation. When you solve it, you will get q1 as a function of time. You could differentiate it and get I1, which will also be a function of time. You will see. Knowing I1 is a function of time means current I1 बदल रहा होगा. तो अगर यहाँ पे डालोगे ये अगर function of time है, मतलब variable है, तो I भी variable आ जाएगा. So I will be another function of time. So all the currents will go a changing. This is like, you know, there is वो कहानी है, कहावत है कि एक खराब मछली, you know, सारे तालाब को. So ये अगर आ गया तो सारे currents को बदलने लगेगा. So these currents will be changing with time, and we can only talk about the current as a function of time. Now this is far more complicated, so you don't have to think about how to solve this differential equation. It's just that much simpler thing we are about to do in what is called as charging and discharging of capacitor. In that we wouldn't have so many things. Okay, so while we are at it, I'll like to take up the fourth element and teach you उसको कैसे handle करते हैं. Because later, few lectures, you know, few videos down the road, we will be doing that. And that is suppose there is an inductor here of inductance L. फिर हम कैसे वहां पे term लिखेंगे? This will come in magnetic field, all this, okay? Induction, induced EMF and all that. So when it comes, you will understand. Maybe we can discuss why you will write that. At the moment, you just have to know the rule. So the rule is the following. I'll write the rule here. Going in the direction of current, include a minus L di by dt term. Now, this automatically means the second rule, which I'll now write in red. Going opposite the direction of current, write plus L di by dt as you encounter an inductor. Okay, so we have now taken care of all the 4 elements, capacitor and inductor, and present chapter, resistor and cell. So we are now done with Kirchhoff's laws. Next is what is called as Wheatstone bridge. Well, a configuration of this kind. Four resistors. Their resistances we'll call by the name P, Q, R and S, and we connect them with a cell like this. What happens? Current goes like this, splits into two, and one stream goes like this and the other like this. They are then joined, they join each other to become the original current. Okay. Now suppose I connect. Under what condition? The question is, under what condition the potential here will be equal to potential here? Now that is very simple, but to save time, energy, effort, I'll just tell you that the potential would be here and here would be equal, provided the following is true. P by Q is equal to R by S. Now in this, you don't have to worry about which by which, because this can also be written as P by R. Bring this here and bring the Q there, Q by S. And you can flip these. So what it means is, you don't have to remember anything, just adjacent ones. This by this is equal to this by this, or this by this is equal to this by this, or this by this by this, similar ones, So do any of these. So if this is true, the potential difference between this point and this point would be 0, because these 2 points would be equipotential. So if you connect a galvanometer here, oh, what's a galvanometer? Galvanometer is just a current measuring device. One design is like this. In subsequent chapters, you are going to learn that a current loop is a magnetic dipole. And this magnetic dipole, just like electric dipole in an electric field, torque acts on it, which tries to align it with the external magnetic field. So what we do is, we take 2 permanent magnets, we hang a coil, and through this coil we'll be sending the current which is to be measured. So what the coil will do, it will try to align with its dipole moment vector in the direction of the field provided by the external magnets. This will create a torque. Now we suspend it through a thread which works like a torsional spring, and so that torsional spring applies a restoring torque. So the coil will not be able to turn so much. If the current is stronger, it will turn through a greater angle. So the current would be proportional to the angle through which the coil turns. And so experimentally checking out the angle through which the coil turns gives us a handle or understanding or measure of how much is the current. The greater the angle through which the coil turns, the greater is the current. So this idea is employed in this device called galvanometer. So if I put a galvanometer here, it will show no current because there is no potential difference. So no current would be flowing. Even if I were to put a resistance here, that wouldn't change anything because there is no potential difference, so there will be no current. Such a scenario is called as null point. Okay, so we say if this condition is true, then the potential here would be equal to here. The galvanometer connected across this is known as bridge, and there will be no current through bridge. And we say the Wheatstone bridge is balanced. We use such language. So what good is it? What can it do for me? Well, it can do something like this. A small numerical. This is 10 ohms, this is 2 ohms, this is 9 ohms, and this is 1.8 ohms, and this is 23 ohms. What current goes through this? Given this is 20 volts. To do this, we notice that this upon this, which is 5, is also equal to this upon this, 5. So this is a balanced Wheatstone bridge. So the potential difference across this and across this is 0. And so no current goes through this. So if you wish, you can remove this. Just remove. Because no current goes through it. And so this is like of no use, you can just throw it out. So for us, this is the circuit. Now, in this circuit, you can say this and this, they are in series, and this in series, and the two elements are then in parallel. Now, this and this in series is 19 ohms, and this is 1/5 of it. Okay. So, overall resistance R is upper one I'll call as R1, R1, R2 upon R1 plus R2. That's the effective resistance in parallel. Now R1 is 19, R2 is 1/5 because each portion has become 1/5. So I'll write 19 by 5 divided by 19 plus 19 by 5. 19 cancels in the numerator and denominator. This 5 would also cancel. So in the numerator, I am left with 19. In the denominator, after cancellation, I am left with 6. So that's the resistance. And so how much is the current? This is V by I. V was 20. So 20 divided by this is as good as multiplied by reciprocal. And that is the answer. 120 by 19. And so this is 6.3 whatever. So many amperes. So these are the kind of things that you can do. Now that we know something about galvanometer, it is a nice time to talk about a few other devices. The first one on cards is ammeter. What we do is we take this galvanometer. The problem with galvanometer is that galvanometer has resistance. Its resistance I'll call by the symbol Rg. So if you take galvanometer and put it in a branch of a circuit, the galvanometer comes with its resistance, and that means the resistance of that branch is changed. So it changes the current. So the problem with the galvanometer directly being employed, one of the problems with galvanometer directly being employed to measure the current in a circuit is the following. The galvanometer has resistance. It comes and sits there with its resistance in series with that element, the current through which you want to find out. So the resistance of that branch is changed. And so it throws a spanner in the works of that circuit. The currents go changing everywhere. For one, this in itself is undesirable. For two, the current in your branch which you wanted to measure has changed. And so the galvanometer walks away with that changed value. But you wanted the original value, not the changed value. So you don't get the correct reading. There are other problems with galvanometer. Things like it is, we have made such a good device out of galvanometer that it is so sensitive that for very small currents it goes full swing, and so it can measure only small currents. All these problems, both of these problems can easily be handled by, if we change, do something to the galvanometer. We take the galvanometer with its resistance and we, in parallel, we put a small resistance. We call it as shunt resistance, and for that this S represents shunt resistance. Then we pack this in a plastic box and we recalibrate this device. What that means is, we'll send 1 ampere current. Since this RS is much less than RG, so most of the current that you send, suppose you send 1 ampere, most of it goes this way and very little goes through the galvanometer. So the suppose out of 1 ampere, only 1 milliampere goes through this. So the 1 milliampere working on the galvanometer makes it swing to this place where the galvanometer earlier, in its earlier avatar, उसमें लिखा हुआ था 1 milliampere. I remove that and I write 1 ampere. This is known as recalibration. So next time I send 1 ampere, most of it goes this way, 1 milliampere goes that way, galvanometer swings to the spot where once upon a time was written 1 milliampere, but now I have rewritten it and I have written 1 ampere. So the person who reads it says 1 ampere. So this is how you get this current. Okay, so that is explaining the meaning of calibration, or rather recalibration. Now this is some current I, out of which the galvanometer can take only maximum this current. For that I am using the symbol Ig. Ig is what? Ig is the maximum current the galvanometer can take. So the balance must be rooted this way, Kirchhoff's first law, I minus Ig. Now the potential difference across this is equal to the potential difference via this route. So I have Ig, Rg is equal to I minus Ig into Rs. This gives me shunt resistance that I must put in to achieve what I want. Rs is equal to Ig Rg divided by I minus Ig. Okay, one numerical is in order. There is a galvanometer of resistance 10 ohms. The maximum current it can take is 20 milliamperes. I want that it should be able to measure up to 10 amperes current, maximum of 10 ampere current. That is, I want it to be of range 10 amperes. So what shunt resistance shall I use? Just plug in the values here. Rs is equal to Ig is 20 milliamperes, 20 into 10 to the power minus 3. Rg is given to us as 10 ohms. So this into 10. I is 10 amperes, maximum current that will ever go through that is the design current for which the ammeter is to be designed, the range on which it will work. And Ig is given as 20 into 10 to the power minus 3. Now, if we have a little idea of sense of arithmetic, we'll say this is negligible compared with 10. And quickly we'll arrive at an approximate answer after neglecting the second term in the denominator. In relation to the heavy duty term 10, we are left, this is gone. So this is neglect in a quick calculation, or unless somebody wants extreme accuracy, it may not be warranted. So you neglect that. So you're left with this cancels with that, and so the answer is 20 milliohms. That thing I have written as 20 milliohms. So that's how it works. Repeating, Ammeter. What is ammeter? Ammeter is a current measuring device. What is its design? Well, an ammeter is nothing but a galvanometer and a very small resistance connected in parallel with it. The whole thing enclosed in a box so that it cannot be changed, and not of course after recalibrating the galvanometer for various levels of current. Okay, so why is this desirable? Because now the resistance of this thing is very small, that is 10 ohms, and as we just saw, RS is approximately 20 milliohms. So much. So what is the overall resistance of these two things in parallel? Well, it is lower than this, because we have the result. Resistance of two resistors in parallel would be less than the lesser of the two. So between 10 ohms and this is less, and so the overall resistance of this thing would be less than this. So when you implant this in series with in a branch of a circuit, then you are not changing the resistance substantially just by this much. So it wouldn't change the current so much, not substantially, and so this is far more desirable than just putting the galvanometer there. Secondly, the galvanometer can take only 20 milliampere, but this device of ours called ammeter can take up to 10 amperes with this design. Okay. Next is voltmeter. Voltmeter is a potential difference measuring device. The current measuring device ammeter, उसको सीरीज में लगाना होता है, जिस एलिमेंट से करंट निकालना है पता लगाना है उसके सीरीज में, और वोल्ट मीटर उसके पैरेलल में. So what is the design? It is nothing but a galvanometer and a high resistance R connected in series. The resistance of galvanometer we'll call as Rg, and the whole thing enclosed in a box so that people won't be able to tamper, but only after recalibrating this. Meaning हम यहाँ पर कुछ 1 वोल्ट का नॉन EMF लगाएंगे, पोटेंशियल डिफरेंस लगाएंगे, देन वील सी ये उसकी वजह से इससे कुछ करंट चलेगा, वो करंट पे ये रेस्पॉन्ड करेगा गैल्वेनोमीटर और उसकी सुई कहीं तक आएगी. लेट्स से इट्स नीडल कम्स अप टू हियर. सो यहाँ पर जितना भी एम्पियर वगैरह लिखा था वो मिली एम्पियर, वो सब मिटा के मैं यहाँ लिख दूंगा 1 वोल्ट. देन आई विल पुट 2 volts and greater current will go, and so it will go there. And earlier in its earlier avatar वहाँ पे कुछ लिखा हुआ था इतने एम्पियर, but I'll write 2 volts. So next time 2 volts comes, same current goes through it and the needle ends up pointing at the same location and the user of our device will read 2 volts. So that's how it works. Only thing is, in this, R is much greater than Rg. Okay, so if you want to measure a potential difference V, then how much should be R? That's very simple. The galvanometer can take only that current that it can, and so the maximum current it can take is Ig. So if I am designing this voltmeter to measure all the way up to V, then at that time a maximum current would be flowing and it would be Ig. At that time, the net resistance across these 2 points is whatever is the potential V, that's the definition, potential V divided by Ig. So the resistance between these 2 points would be V by Ig, and from that you subtract Rg, and you get this resistance. So yeah, so a numerical on this is in order. Take this resistance of galvanometer, once again like last time, this R, the resistance here, you have to find out. The maximum current that it can take, once again the same value we can take. Did we take 20 milliamperes last time? 20 milliamperes. So हम वही वाला galvanometer use कर रहे हैं, only this time we are converting it into a voltmeter. But we want that the voltmeter should be able to measure all the way up to 100 volts. What resistance R shall I put in series? Plug in the values. So V is 100, Ig is 20 milliamperes. I write the milli as this. So since this is in ampere and this in volts, this will come out in SI units, that is ohms. And Rg is well given in the problem as 10. Now this is 20,000. This alone, sorry, this 20 cancels with this, giving us a 5, and this jumps there, 1000. So 5,000. From that, I can, if I don't want, an exact value, I can say 5,000, else I can say 4,990 ohms. So that's the resistance that I have to put in series to convert this galvanometer into a voltmeter, which will be capable of measuring up to 100 volts. Okay, maybe a little discussion on some circuits with symmetry, in mind is in order. So we are going to discuss symmetry in circuits, how it is exploited to spin out smart solutions. Symmetry. Imagine somebody has given us this problem to solve. In this, there are 12 wires. Okay, maybe the black ones have resistance and the red ones are lead wires. Okay, and this is A and B, and these 12 wires in the hexagon, 6 on the sides and 6 radial wires, all of them have resistance R each. So 12 wires, each of resistance R. Okay, and we have been asked to find out RAB. This is copper wires, it has no resistance. So between A and B, what is the resistance? Now there is a problem. Let's think, the current that comes this way, it is splits into 3 parts. Some of it goes that way, some of it this way, some of it this way. And that current, so are these 3 in parallel? Certainly they are not in series. Are they in parallel? Well, not even so, because between this and this, although the left end is joined together, and so this and this, their left end is equipotential, but the right end is not, because there is a current going through this, so there is some potential difference between here and here. So this point and this point, they are not equipotential, and so this wire and this wire are not in parallel. In fact, no 2 wires here are in parallel nor in series. All our parallel series scheme is blown. How do we handle this? Like this. Can you see? Because of symmetry, okay, can you first see, as I move this way, ऐसे आगे आगे सोच रहा हूँ, आगे आगे जा रहा हूँ, तो यहाँ पर सपोज मैंने यहाँ पर ऐसे एक सेल लगाया हुआ है और सोचोगे ये 100 वोल्ट्स का है, तो जैसे जैसे आगे बढ़ रहा हूँ पोटेंशियल ड्रॉप कर रहा है. Suppose I call this as 0, then this is 100 volts. Okay, this 100 volts is as good as calling this as 0 volts and this as 100 volts. Can we see कि आगे बढ़ने से जैसे जैसे आगे जा रहे हैं, क्योंकि करंट इधर जा रहा है, so this must be higher, this must be lower. तो आधे रास्ते पर यहाँ पे आने पे potential would be sitting pretty at the level of 50 volts. This is symmetry. By symmetry we can say फर्स्ट हाफ जैसा था, जो सीन था वही सेकेंड हाफ में है. So there is no reason why potential should drop through a greater value here than there. So it will be equal. And so this point, and this point, they are all equipotential. Okay. The points marked in small red crosses are all equipotential. Midpoint of that resistance and the central point here and this, they are all equipotential. Now, suppose maybe I should draw this in a separate diagram. So our red lead wire, end A, then the hexagon, the other wire, and what happened to those two? I'm drawing them, don't worry. So ये वाले दो वायर रह गए, अभी उनको भी बनाता हूँ. सपोज मैं इसको थोड़ा सा ऐसे दबा दूँ, स्क्वीज कर दूँ ऐसे, और वो ऐसे झूल जाए नीचे. Does the resistance RAB change by कि सीधा तार जाने की जगह थोड़ा सा ऐसे दबा हुआ आ जाए? No, the resistance is the same. So resistance doesn't change. Okay. So encouraged by this, you may say, I decide to do that act a little more. And so मैं थोड़ा और इसको प्रेस कर देता हूँ और ज़्यादा. So ये ऐसे हो गया. Does the resistance change? No, it doesn't. Because this is still R and this is R, and so it's the same. आप उस resistance को सीधा लगाओ या ऐसे लगाओ, electrical connection is the same. So it's the same circuit, nothing has changed. So resistance RAB doesn't change. And suppose I squeeze it further and further until now this happens. It connects here, joins. And this also connects. And let me clarify. The point which I have connected are those red points, the mid points, not some other points. So I keep squeezing and those mid points are connected. Does that change the resistance RAB between points A and B? You may say, sir, jab tak you hadn't touched, koi alag scene tha. Now you have touched, this is different. And so I don't know, I don't think this is the same as this. The thing is, if you show this to somebody by symmetry, will they say, if you show this, they'll say this, this and this, they are equipotential. Now the same 3 points, they are equipotential because the bottom point of that, notch here, this one, and this one, and the central point here, this one, they have physically, touched each other, and so they have become equipotential. Okay, but they were already equipotential even there. So I have really not changed anything. So this circuit is equivalent to this. When can you do, now this trick, I call it by the name squeeze trick. You can squeeze them and touch them. When can you do that? When by doing this, if you touch them, they'll become equipotential. Whichever points you touch, they'll become equipotential. So if they were already equipotential, then you haven't changed. So what you have to do, is your squeeze all right? For that you revert back to the original diagram and say, before the squeeze, were they equipotential? So since I have connected the midpoints with this, so they were already equipotential by symmetry, and by touching them, they still remain equipotential, nothing changes. However, the problem has changed drastically, and now my solution is simple. This is R by 2. This is R. This is R. The central part is R, and I don't have to compute, even talk about the right side, because symmetrically the resistance of this is the same as on the left. So my plan is to compute the resistance on the left and then double it, because the right half is in series. To compute the resistance on the left, this and this, they are in series, parallel, and that they become 1. How much will that be? Let me compute. I'll use the formula R1 R2 upon R1 plus R2 unleashed on R and R2. So it becomes R1 R2 upon this plus that. Let's do that orally. So that's 3R by 2. the r by 2 cancels. So it is r by 3. This whole thing, this 2 sum, this part, this one is r by 3. To that, r is to be added in series. So I'll add r here only. So what does it give me? R by 3 plus r is 4 by r by 3. So this upper portion, all this, is 4r by 3. And lower one is as much, symmetry again. So 4r by 3 and 4r by 3 and this, all three are in parallel. But I'll do, like this. I'll use this and this first and make one out of them. Now if two resistors, equal ones, are in parallel, everybody knows the resistance would be halved. So when these two are combined, then the resistance becomes half of this is 2r by 3. And then that is to be connected with r in parallel. So I take this and I take r and do r1 r2 upon r1 plus r2. Think plus, so I get 5r by 3. So this time r by 3 cancels out. So I am getting 2r by 5 so far. Now that represents the resistance of the left half, but as much as the resistance of the right half. So the answer is RAB is 4r by 5. So that is our squeeze trick to be used in situations such as these where symmetry helps us know that certain points are equipotential. If you do find that, you are free. If it helps you solve the problem, if it eases the solution, makes it easy, go ahead and squeeze them together, physically bringing them to a single point as there. So this trick I'll call as a squeeze trick. Now, let's learn another trick by using this same problem. Suppose I'm given the following question. And somebody says, this side resistance is R, that is R, this is R, this is R, this left is R, this is R, and all others are also R. And somebody says, what is RAB? You see, one thing I could do is, since by symmetry, this, they are all equipotential. So if I want, I can squeeze them all together. If I want, I can, squeeze just these three together. So suppose I squeeze these three together. What do I get? I get the original problem. I get this if I squeeze them together. These 3 points, if I squeeze them together, I get this. So will I do this? No, I won't. In fact, as it is, the problem is fine. However, if this can be squeezed, then the squeeze thing can be done like that. Now this I call as unhook. Because these things were hooked there, I can separate it. So what I do is, if I get this problem, here is a second solution. I write that, I think of this like this. I unhook like this. I separate them like this. And then what happens? This is 2R and that is R. And this is R and this is R. And the central line is 2R. And the lower we'll use the same as upper. So everything is in series and parallel once again. Let's check whether answer is the same. Now this part is parallel between R and 2R. So this is R1 R2 upon R1 plus R2 gives me R1 R2 upon, think plus, so this is this, 1R cancels. So this part, this and this is 2R by 3. That 2R by 3 and this R, that is 2R, are in series. So overall upper thing, this overall thing, its resistance, let's compute. How much is that? That's equal to 6R and 2R, 8R by 3. Now this upper is 8R by 3. So is the lower part. So two resistances in parallel, and this also is in parallel, but let me first add these two. So they become 4R by 3 halved. Now this and this has become a single one equal to this, and that single one is in parallel with 2R. So again I apply R1, R2. This is R1, R2 upon R1 plus R2. Think plus. So we have got 6 and 4, 10. 10R by 3. Okay, so that's RAB is equal to RAB. Let me calculate what have I got. The R by 3 here cancels off with the R by 3 here. A 2 cancels out. So I am getting 4R by 5, which matches with the previous found out answer for RAB. So we have two tricks. The squeeze trick, you can squeeze this problem, you can squeeze, or you can unhook. You can do that. You can say, oh, I like to separate these. Okay. Both of these tricks can be used for the celebrated question of cube of resistors. So there's a cube of resistors. Let's say across the body diagonal we take the tappings A and B. So how much is RAB? Once again, each edge represents a resistance of R. Since there are 12 of them, I'll put it like this, each having resistance R, and question is how much is RAB? I'll leave it for you to do it by the ideas of a squeeze and all that. But here's another idea. This is redrawing the circuit diagram, and just to, okay, this is some level of potential here. This is some other level of potential. So what I do is, corresponding to this, I give it a name. I call it as VA. So this is VA level of potential. The other end here or here, it's the same VB level of potential. And now which of these are equipotential, these corner points? Look, if current I comes in, then by symmetry it goes equally into 3 branches. So this will be I by 3, I by 3, I by 3. This and this. Each one would be I by 3. So working through the resistor, its way through the resistor R, the potential will drop by I by 3 into R. And here by the same amount and same amount, starting from a common value, dropping by equal values, it will end up being equal here, here and here. That equal potential, okay, I call it as, I indicate it by cross level of potential. Now I had to argue in terms of I by 3, I by 3, I by 3, because it is in 3D, it is more difficult to see that these points are symmetrically similar and therefore the potential would be same. But you can do that by putting that cube like that and having a look like this, and you can see down all the edges that's the same story, and so the potential here would be equal. Similarly, potential at these points shown by red solid circles is also equal between themselves, amongst themselves. So I'll call that, which will be still lower level of potential here. So I've organized potentials from a high level VA down to low level VB. These 3 points at the cross level is still lower down at the circle level. Now, this technique you are not seeing for the first time. You also saw that in the previous video on capacitors. Only it might look a little different. The thing is, if you think about this resistor, this one, concentrate on this resistor. Do you see this resistor? Its 2 arms are connected to 2 levels of potential. One is VA level of potential, the other is cross level of potential. So you capture the electrical truth of that connection by drawing that resistor whose resistance is R between VA level and cross level. So I draw one resistor between VA level and this, its resistance is R. And now look at this. This is also, its two arms are one at the cross level and one at the VA level. So I draw that resistor, this one. And there's one more. There are three such resistors. So I draw the third one. So that takes care of these three. Okay. Then I'll maybe go from the other end. This resistor and this resistor and this, their two arms are for each of them connected on one side with this circle level of potential, on the other side VB level. So I draw three resistors here. Now how many were there? You see there are 12 sides, and so 12 resistors, out of which 6 have been connected. 6 more are left. But I have already used up, those resistors which are between VA and cross and VB and circle. So since there are only 4 levels of potential, VA, circle, cross, circle and VB, so the only ones which are left are between cross and circle. If you carefully check them out, you will see that yes, they are. I'll label them. There are 6 more of them. Each one, their two hands across cross level and circle level. Let me number them so that everybody in the count is verified. This is 1. This is 2. Both are horizontal and in the top plane. And this is 3, horizontal and bottom plane. And this is 4, horizontal and bottom plane. And 2 vertical ones. This 5, vertical, hind edge, vertical edge, and front vertical edge, 6. These 6 resistors, their two hands are between cross and circle. So I draw hurriedly, quickly, I draw 6 more. 1, 2, 3, 1, 2, 3. And all of them are of resistance R each. So what's the resistance between points A and B? Okay, these 3 become R by 3. These 3 become R by 6. And these 3 become R by 3. And the 3 pieces are in series. So RAB is equal to this. And so we get, make the denominator equalize it at 6, level of 6. So this becomes 2R, and another 2R, 4, and one more, 5R by 6. So that is the answer. Of course, this answer can be found in other ways, as I told you, but okay, we just looked at this technique. Fine class. I think you must have enjoyed it and got something to learn on the way also. Thank you.